Okay, in the last class we were discussing about the basics of op-amp. So today also we will see what are the three different configurations of op-amp. So in this op-amp, so we can consider there are three different configuration by employing a negative feedback. So whenever one of the op-amp output terminal is given to the inverting inputs, then that type of feedback is called as a negative feedback. In this negative feedback, we come across three configurations. One is non-inverting configuration, inverting as well as the voltage follower. So what is non-inverting configuration? You can see that the circuit symbol here is the op-amp, in which for the terminal B, wherein which we are giving input signal to the non-inverting terminal, and the output of the voltage of the op-amp at terminal 6 is being applied to both of the resistors. So RF and R1 together, it is nothing but a feedback network. In that, the voltage drop across R1 will be given as a input to the inverting terminal. So this type of configuration or this type of circuit diagram, so wherein which the non-inverting terminal input is applied and the output is through the feedback resistor. So it is being given to the inverting input. Then this type of configuration is called as a non-inverting amplifier. So in this non-inverting amplifier, you can see the input signal is applied to the non-inverting terminal. So what is the gain of the closed loop gain of the operational amplifier for non-inverting amplifier? We have to calculate. So for this, already you are familiar in the basic electronics. So what is the non-inverting amplifier gain? So non-inverting amplifier gain AF is given as that is V naught will be equal to 1 plus RF by R1 times of V in. So that is what the that is what the expression for negative feedback. So we'll see how it is going to happen or how we are going to calculate. So when we consider this, so the inverting input, so the non-inverting input, we are applying input signal. That input signal is being amplified and it is going to produce as the output voltage V naught. The output voltage V naught is completely available between this terminal 6 and the ground, so that the output voltage will get divided across the voltage across. So some voltage drop will occur across RF and some of the voltage will have a drop across R1. So you can see that the current flow is through the direction from the output terminal 6 to this one, so that you can see the current flowing direction is being given over here from this potential towards the ground. And here we can see what is VA and VB. So here VA and VB both are at the same potential. Ideally we have seen, so the terminal, in order to equalize the current that is flowing across the terminals at the input terminals, that is inverting and non-inverting, IB1 and IB2. So both the current must be same. So in order to equalize this, so we are assuming that the current at the potential at this node A and B both will be same. So here we can see that VA will be equal to VB is equal to V in. Why? Because to equalize the current that is flowing here. So the inverting terminal, the current flowing is IB1, and non-inverting terminal, the current flowing will be IB2. So both the IB1 and IB2, so it should be equal. So whatever you apply the inverting voltage across the non-inverting terminal V in, the same V in will be appearing across here because of the potential. So we know that virtual ground concept, the same way the terminal node A and node B must be at the same potential. So node B is at V in potential, means the node A should also be at the V in potential itself. So that means the voltage drop across R1 must be equal to V in, and the remaining voltage will be appearing across the RF. So using that virtual ground concept, so you can see the concept of virtual ground, we are going to equalize the voltage across node A and node B as same as that of V in. And from here we can see the remaining output voltage, how much the voltage drop. So we are going to calculate. So what is the current that is flowing in this the feedback loop? That is I is the current flowing and V naught is the output voltage. So I is equal to V naught minus VA divided by RF. So that is nothing but a V naught minus VA by RF. So V naught minus VA divided by RF is nothing but the current that is flowing as I. So that is the I is equal to V naught minus VA divided by RF. So we know that VA is nothing but V in. So V naught minus V in divided by RF, that is not the voltage. And when we look at the inverting terminal, so also we know that the inverting terminal potential, there will be no current flowing across the inverting potential because of the load, that is a virtual ground concept, and hence we can say that all the current that is flowing on the from the output terminal, it is going to flow through this path because the input resistance of the op amp is very high. That is such a, for that reason all the current effectively will be flowing across the RF through R1, not flowing through this one. So because of the high input resistance, so we can say that V0 minus 0, so that is what is that, V in across the node potential. So since there is no current, there will be no voltage drop, so V0 minus V0 by R1, so we will be having the current I will be equal to V in by R1. So the same thing if you equate the equation, so V0 minus V in divided by RF, and here this is the potential at this is 0, 0 minus VA divided by R1, so that is nothing but V in by R1, so that is what the equating, so that the current will be equal. So now using these two concepts, you can see that if I substitute the value for the RF, so you can see that V0 by RF minus V in by RF will be equal to V in by R1. So making these two concept, because both are having V in term, so we can make take it in the right hand side, and we can make it as a V0 as the left hand side, and remaining only we will through expression V0 will be equal to RF multiplied with this one, so you will be getting the expression as this. So output voltage expression is given by RF into V in R1 plus RF divided by R1 RF. So this together if you consider, then it is nothing but a together if you simplify this expression, you will be getting the equation for the closed loop gain. So AVF will be equal to V0 by V in, that is AVF is nothing but voltage gain with feedback for the non-inverting amplifier is given by V0 by V in will be equal to 1 plus RF by R1. So this is the closed loop gain of a non-inverting amplifier configuration. So this is what we have seen. So the gain expression if you consider, so it will be always greater than 1. So you can see that 1 plus RF by R1 is there. Any value of the RF and R1 resistance, if you change also, the gain will be having 1 plus RF by R1. So that means you will be having the mode. So both will be having the same phase. If you see the output voltage and input voltage, so since the non-inverting input I am giving the input signal, this is the input signal. Since this signal is given to the non-inverting terminal, so output terminal voltage will also be having the same phase, but the gain will be high. So the gain will be high means the gain will be equal to 1 plus RF by R1 times of the input voltage will be getting as the output voltage over here. So this is what the input and output voltage waveforms of a non-inverting amplifier. The same way if you want to consider for the comparison of ideal inverting and non-inverting amplifier, so you will be having this gain. So inverting amplifier gain, it will be having minus RF by R1, so that is a negative feedback gain for inverting amplifier, and the minus sign in the gain expression leads to that that whatever you give the input signal, the output signal will be 180-degree out of phase. So that is what the gain, so the minus sign indication is nothing but out of phase, 180-degree out of phase, and it will be equal to RF by R1. And the voltage gain of a non-inverting amplifier is 1 plus RF by R1, and the output is inverted because it is an inverting amplifier, 180-degree out of phase, and also the voltage gain can be adjusted by greater than, equal to, or less than. So equal, so if RF and R1 is, RF is greater than R1 means the gain will be greater than 1. If RF is equal to R1, then I can control the gain of the voltage gain of an inverting amplifier. If RF and RN are both are same, then the gain will be unity gain, that is minus 1 you will be getting. If RF is less than R1, then the resistance, if RF resistance is less than R1, then you will be getting less than 1 gain. So this is what the ways in which you can control the gain. But in this case of a non-inverting amplifier, even if you consider RF is greater than R1 also, you will be having greater than 1. RF less than R1 also will be greater, will be getting greater than 1. That means you will be having more than 1 gain in this non-inverting amplifier configuration. So wait a minute, I will just continue. ಒಂದೇ ನಿಮಿಷದಲ್ಲಿ ಇರೋ ಡಿಸ್ಕಾರ್ಡಲ್ಲಿ ಒಂದು ಫೋಟೋ ತಗೊಂಡ್ಬಿಡ್ತೀನಿ. Okay, so we were discussing about what? So we were discussing about the inverting, the comparison between the ideal inverting and non-inverting case, and here you can able to control the gain. So for the given circuit, you can see what is the configuration given. So in the given circuit, you try to solve one numerical. So in this, for the op-amp configuration, the gain requirement is 61. So that means the gain is 61. Determine the appropriate value of the feedback resistance RF. So here given one of the resistance R1 is 1 kilo ohm, and it is, you can see the out from the output one RF feedback resistance has been given to connected from the output to the inverting input, and you can have to notice that input signal is being given to the non-inverting terminal. So the op-amp configuration, you are going to consider it as a non-inverting amplifier because input is being given to the non-inverting terminal, so that it is a non-inverting amplifier configuration. The gain of the non-inverting amplifier, first you should know. So the gain of the non-inverting is given by what? So V0 by Vin will be equal to 1 plus Rf by R1. He has asked you to calculate the value of the feedback resistance. So 1 plus Rf is unknown term. R1 is given as 1 kilo ohm. So you can see that 1 plus Rf by R1 is equal to 61 because the gain is already given as 61. So the gain of this configuration is given as 61. So you can see that Rf by R1, Rf by 1 or Rf is equal to 60. So 60 kilo ohms because you're going to have the gain as 61, and you can see that 1 is being given over here. 1 plus 60 is nothing but 61. So the same way RF is made as 60 kilo ohms. The same thing you can see in the second circuit which has been given. Find the output voltage for the circuit has been asked. So here you can see the input is being given through the potential divider resistor 1K and 1K is there. So 10 volts I am going to apply here. But what is the effective voltage across this, we need to find out. And here 50 kilo ohms and 10 kilo ohms is being considered as a feedback network, RF and R1 respectively. So this will be considered as what? So this will be considered as the non-inverting amplifier configuration itself. But the 10 volts whatever you are giving, but it is going to appear at the non-inverting, how much voltage we need to find out first. After that we can say that for the given input non-inverting amplifier configuration you can consider. So 10 volts will get divided across 1K and 1K means, so it is, since both are having same equal resistance, so you can say that here 5 volt drop and here 5 volt drop it will be there. So the 5 volt will be acting as an input to the non-inverting terminal, and this 5 volt will be amplified by this gain 1 plus Rf by R1 times of 5 inputs volts. So you'll be getting as a 5 into 1 plus 50 by 10. So that is 50 by 10 is nothing but 5 only. So 1 plus 5, 6 into 5, 30. You will be getting 30 as the output. So you can see here the same thing you are going to get as the output for the non-inverting. So for that, how we need to calculate is this 10 volt, how much it is coming to this point B, we need to find out, because this point B is the voltage, input voltage of the non-inverting terminal. So we need to find out what is the voltage across this point. So in order to understand this point, so 10 volt into 1K divided by 1 plus 1, if you calculate, then you will be getting 10 into 1, 10 divided by 1 plus 1, 2K. So that is 5 volts will be getting at this point. This 5 volts will be amplified. So you will be getting as what? So 5 volts, so you will be getting that 5 volts multiply with 1 plus 50 by 10. So 50 by 10, that is 5, 5 plus 1, 6, 6 into 5, 30. So you will be getting 30 volts. The same way, so in order to understand the next the concepts is inverting amplifier. I think I have skipped that inverting amplifier configuration. So the inverting amplifier configuration is also going to work like that only. So inverting amplifier. So you can see that inverting amplifier configuration. Here you can go through this circuit. So inverting amplifier configuration. Okay, so in the next class I will just do about the inverting amplifier configuration. Now we will understand. Already we have discussed about the feedback types that can be given for a voltage op-amp amplifier, operational amplifier. So there are typically two ways that is you can give. One is positive feedback, another one is a negative feedback. Whenever the output is being given to the inverting input terminal, then that type of feedback is called as negative feedback. And whenever the op-amp output is being connected to the non-inverting terminal input, then that type of feedback is called as positive feedback. So now you'll understand the feedback configuration. Already we have seen in the third module of the feedback structure. So wherein which the top of the is called as amplifier, and the next is the feedback circuit. The same way here also you're going to have the top is nothing but operational amplifier, which is nothing but a open loop, that is a open loop amplifier, that is op amp. And for this op amp, so if I'm going to connect a feedback circuit, so you can have feedback. So this entire thing will become what? It is a negative feedback. For now we are going to concentrate on the negative feedback, and we are going to see what are the different steps we are going to have. So we know that depending upon the type of the signal at the input and output, so we are going to have four different ways. What are the four different ways? One is series, shunt, series. So four different configuration. So depending upon the type of the input signal. So already we are familiar that input signal, if it is a voltage and the output is voltage, then the configuration is called as what? Voltage amplifier. So this the output will be voltage and the input is also voltage. So we'll be having a voltage. We're going to call that as a voltage amplifier. If the input is voltage and the output is current, so then current the ratio of output current to the input voltage, so we are going to call it as what? I by V. So that is a trans resistance amplifier, trans conductance amplifier. So there is trans conductance. So if the input is current and the output is also current, then current is being amplified at the output side. So that is called as a current amplifier. And if the input is voltage and the output is current, sorry, if the input is current and the output is voltage, then that called as a trans conductance, trans resistance amplifier, V by I. So it is a trans resistance amplifier. So here the main amplifier stage, how the signals are being connected at the input side, and how the input is output from the output, how the feedback for the feedback network, how the sampling of the from the output of the amplifier is being connected to the feedback. So depending upon the time, so we are going to call it as a sampling at the output side, and the input side is the mixing type. Mixing of the signal at the input side, and the output we are going to take the sample. So in that case, so we are going to call we will call different four configuration. So in that case, we know that whenever we need to take the sample of the output voltage, always we need to connect in the parallel way. So parallel, that is shunt across the output side, and whenever we want to mix the voltage across the input side, then we have to mix in the mixing of the voltage takes place whenever it is being connected in series. The sampling of the voltage will be taken place in the parallel way. So you will be having what? Voltage is being connected, it is taken as the sample, and across the input side it is being connected in series. So it will be called as a voltage series feedback. So this voltage is being connected in series at the input side. So the configuration is called as a voltage series configuration. So typically this for this application is nothing but a non-inverting amplifier configuration. So in this case, you can see the output is voltage and input is also being connected as a voltage. So we are going to call it this as an amplifier as a voltage series configuration. And at the voltage shunt configuration means we are going to have the voltage sampling is going to take place at the as a parallel, whereas the output input to the signal is current, means we are going to mix in parallel way. So whenever we are going to give the input in input in current, input signal is current, and output you are going to get as a voltage, then the input signal from the feedback signal, it is going to be mixed to the input side in a parallel way, and hence mixing of the current takes place in parallel, and hence the circuit configuration is going to be called as voltage shunt configuration. So for this typical example, you have to voltage shunt configuration means you have to consider the inverting amplifier of the op amp. So inverting op amp, that is wherein which input signal will be current, output is nothing but a voltage. Whereas for an voltage series configuration, you have to consider that input is also voltage, output is also voltage. That is for a non-inverting amplifier configuration, you have to consider. Voltage series means non-inverting amplifier. Voltage shunt means it is inverting amplifier as an example. So voltage series feedback. So we'll learn what is the in depth about the voltage series feedback amplifier. So voltage series means what? It has to be non-inverting amplifier. In general, you have to consider. So you are going to consider this as the main amplifier, and this is the output. From the output, we are going to consider to the feedback network. This is the feedback network RF by R1. So that is the feedback network we are going to have, and this is the non-inverting amplifier configuration because it is voltage series configuration. And the voltage across the R1 is given as input to the feedback to the inverting terminal. So this is the voltage across the feedback is given as input to the inverting terminal. And as I told, so input stage is made up of differential amplifier, so it is going to be connected in series fashion. So voltage is being mixed in the series fashion at the input side, whereas voltage is sampled at the output, that is in connected in parallel fashion. So you are going to get as a this as the feedback voltage. So this is nothing but in the output side it is parallel, at the input side it is in voltage is being connected in series. So this is the input voltage that is being connected in series with the VF at the input side. Mixing of the voltage is taking place between the Vin and the VF at the input side, and sampling of the output voltage is being sampled in the parallel way. So that is VF is taken from the output voltage in a parallel fashion. So this configuration is called as voltage series feedback amplifier. So this VID corresponds to what? Differential input voltage. So differential input voltage means here you will be having V1, it will be as V in, and V2 is nothing but a VF. So this V1 minus V2 it is going to have, because I already told, so input stage is made up of differential amplifier. So differential amplifier means two inputs will be there, one is from V1 and another one is from V2. So V1 difference V2 only it is going to be taking place between this, and this VID will be amplified in the intermediate stage, and finally you will be getting at the output. So V1 minus V2 means, so it is nothing but V in minus of VF, so that is going to be taken place as VID, and this VID is nothing but differential between the input terminals, so V1 and V2. So that will be amplified in the intermediate stage to get the final output across the load resistance, that is the V0 across RL. So we are going to see how the closed loop gain. So already we are familiar. So amplifier, so it is the main top is nothing but amplifier, and bottom circuit which is made up of passive component is nothing but a feedback circuit. So open loop voltage gain. So open loop voltage gain means this is a op amp is nothing but an open loop gain. So for this amplifier gain or gain without feedback, we are going to have what? So V0 by VID. So that is nothing but a open loop amplifier gain. So wherein which we are not considering any feedback signal. So V1 minus V2, that is the difference between these two is nothing but acting as an input. And so V0 by VID, that is nothing but a open loop gain. So now if I want to find out what is the closed loop gain, so closed loop gain is given by what? So AF. AF is nothing but gain with feedback. So gain with negative feedback, gain is closed loop gain. So we are going to call it as AF. AF will be equal to, so total output voltage versus the input voltage. So that will be called as the gain with feedback. So gain with feedback, AF is equal to V0 by Vin. And now what is the gain of the feedback circuit? So this is the gain of the feedback circuit. What is the gain? So gain is what? So the output of the feedback is VF, input to the feedback circuit is V0. So V0 will get divided. So what is VF? VF will be equal to what? V0 into R1 divided by R1 plus RF is nothing but the feedback. So VF is the output and V0 is the input, and this is the gain of the feedback circuit. So now if I want to have negative feedback, so we already know that VID is nothing but V1 difference of V2. V1 is V in, and V2 is nothing but Vf. So V1 minus of Vf, that is nothing but VID. So that is the differential input voltage across the two input terminals. So non-inverting and inverting. What is the voltage drop we are going to get? So that is VID. That will be equal to V1 minus of V2. So V1 minus of Vf. ಯಾರು ಕೊಟ್ಟಿದ್ದು ಇವರೇ ಸರ್ ಪೆನ್ ಇಲ್ಲ ಹೌದು ಬಾಕಿದೆಲ್ಲ ಕಾಣ್ತಿಲ್ಲ ಸರ್ ಹೇಳೋದು ಸರ್ ಎಲ್ಲೋದ್ರಪ್ಪ ಗೊತ್ತಿಲ್ಲ ಕ್ಲಾಸ್ ಇದೆ ಮೊನ್ನೆ ಮಾಡಿಸ್ಕೊಟ್ಬಿಟ್ಟು ಎಲ್ಲ ಹಾಕ್ಬಿಟ್ರೆ ಗೊತ್ತಿಲ್ಲ. Okay, next is we'll be seeing what is how you are going to find out the calculate the gain for voltage series feedback. So VID is given by Vin minus Vf. So Vin is the voltage across the input, that is mixing at the input side. So Vin minus of Vf is nothing but output voltage of the feedback. So that is being mixed. So Vin minus Vf is the difference between the input voltage. And now closed loop voltage gain. So in order to find out closed loop voltage gain, so AF is given by what? V naught by Vin. So this is negative feedback and this is the output closed loop gain. So V naught by Vin. So V naught is what? So V naught is the output voltage which will be equal to A times of VID. So VID is nothing but V1 minus V2. So A times of V1 minus V2. So V1 is equal to Vin and V2 is nothing but the feedback signal. So that is a Vin. Vf, right? So V in minus Vf. So V in minus Vf. So V in minus Vf is nothing but what? V naught into R1 divided by R1 plus Rf. So that is a feedback signal. So if I substitute the value of this, so you'll be getting the negative feedback gain A into V in minus of V naught minus V naught into R1 divided by R1 plus Rf. So if you substitute this expression, so if you elaborate this R1 plus Rf at a denominator term, this will get multiplied V into R1 plus Rf minus R1 into V naught, and if you substitute, this is being multiplied A V in R1 plus A into V in into RF minus A into R1 V naught divided by R1 plus RF. So this is the V naught term is there. So here also V naught term is there. Separate the V naught and V in term. So here left hand side will be all V naught term, right hand side will be all V in term. So you can see V naught plus A times of R1 V naught divided by R1 plus RF. Here all V in terms will be there, A into V in divided by R1 plus RF divided by R1 plus RF. So you will be getting its cancels. And if you consider V naught by V in, so you will be getting A into R1 plus RF divided by R1 plus RF plus A times of R1. So this is the exact analysis, but what we got is that so we are going to get exact analysis. So when we look into the expression for negative feedback for the non-inverting amplifier gain, so we will be getting as what? 1 plus RF by R1. But here you are going to get this as something different, right? So R1 plus RF is equal to what? So here we can make it as A times this is the exact analysis. Always you should remember that the A is nothing but the open loop gain. Open loop gain of the amplifier will be always greater when it is being multiplied with R1. So the denominator term, if you consider A times of R1, will be usually greater than R1 plus RF, right? So this R1 and RF will be in terms of kilo ohms, whereas here the gain of the op amp will be very high, open loop gain, when it is being multiplied with R1. So obviously this denominatorly A times of R1 will be always greater than R1 plus RF. So when you can see that R1 plus RF together, it will be in terms of kilo, whereas here it will be in 10 power 6 or 10 power 7 if it is there, then hardly. So this will not have any contribution. So we can easily neglect this R1 plus RF in the denominator term. So we will be left out with what? A times of R1. So A times of R1 will be greater than R1 plus RF, means you can neglect this, and this A will get cancelled. Then you will be having what? R1 plus RF divided by R1. So R1 plus RF divided by R1. So together R1 plus RF divided by R1. So then you will be having the equation for ideal value as 1 plus RF by R1. So this is the negative feedback gain for a voltage series feedback amplifier. The same thing we have learned. So that is the what is the gain expression for ideal is 1 plus RF by R1. Exact analysis if you want. So this is the value of the expression you will be getting as an exact analysis. So now if you can consider the gain of the feedback circuit is given by B as the ratio of the feedback output voltage and input voltage to the feedback. So B is what? So feedback gain, right? So normally we are going to have what? So feedback circuit means output voltage is VF. So that is for the feedback output voltage is VF, for the input of the feedback circuit is being given from the output V0. So VF by V0 is nothing but the feedback gain. So when we consider the feedback gain VF, what is VF? VF, we know that. What is VF? VF is nothing but V0 into R1 divided by R1 plus R2 divided by V0. So if you calculate, so they'll be getting the gain as expression. So VF by V0 is nothing but V0 will get cancelled and it will be R1 over R1 plus R2. So if you clearly look this and the gain expression of this, so both are same. So AF will be equal to what? 1 plus RF by R1 is nothing but R1 plus RF divided by R1. This, and if you consider this R1 plus RF divided by R1, so you can see that amplifier, open loop amplifier gain and feedback gain both are opposite. That means both are what do we call? So we are going to call it as what? So both are equal and magnitude but opposite in direction. So you can say that A is equal to R1 plus RF divided by R1. So beta gain is nothing but R1 divided by R1 plus RF. So you can say that the feedback gain is inversely proportional to the feedback negative feedback gain. So this is a negative feedback gain will be equal to inverse of the gain of the feedback circuit. So 1 over B. So you will be getting as 1 over B for this one. So this is about the voltage series. So similarly, if I want to find out with respect to the exact analysis, so this is the exact analysis of the non-inverting amplifier gain. So AF will be equal to A times of R1 plus RF divided by R1 plus RF plus A times of R1. So this is the exact analysis. So if I subtract, if I take the numerator as well as the denominator, if I take division divided by R1 plus RF, so you can see for the exact analysis, R1 plus RF divided by, so together we are going to splitting these two and we are going to have R1 plus RF numerator and denominator, so it is going to remain same, right? So here the entire thing I can make it as 1, and here the entire thing I can write it as what? A into R1 divided by R1 plus RF. This I can write it as beta, so A into B, and here you can see this is 2 gets cancelled and you will be having A. So this is the gain of the negative feedback. So through this we can say that whenever the output is being connected to the negative inverting input, so the feedback will be considered as a negative feedback. So we are just cross verifying whether the gain which we are going to get is a negative feedback gain or a positive feedback. So using this concept of exact analysis, you can say that negative feedback gain will be confirmed by this expression A over 1 plus A into beta. So this is what the negative feedback gain. So this with this I can write the generalized this block diagram of the voltage series feedback. Vin is the input, so it is being given through this one, and the feedback network is nothing but R1 and RF. So that is VF is giving subtracting with this one. So plus and minus if it is there, then Vin minus VF, that will be equal to the VID, that is the difference between the two input signal at the op amp input, and for this main amplifier is op amp. This will amplify the input signal VID and it is going to provide output voltage V0, and from the output voltage we are going to give it as input to the feedback circuit. So through this we are going to see that the block diagram of the voltage series feedback of the amplifier, or block diagram of the non-inverting amplifier with feedback. So non-inverting amplifier diagram with the feedback. So this is about the voltage series feedback. So with this I will just conclude today's session, and in the next class I will be starting with the voltage shunt feedback configuration. So voltage series feedback, 10 marks definitely they will ask this question, or else they will ask one numerical, when the small numerical can be asked in this section. Any doubt is there? Hello, whether my voice is audible? Chinmay, Komala, Adarsh, Naveen, Akhilesh, Yogesh. None of you are responding.
Yes, sir.
Yogesh, Unmute your mic. Yogesh.
Yes, sir.
What topic we have discussed today? Unmute yourself. Komala. Komala.
Yes, sir.
Thumbs up Madrala. So you tell me what is the topic which we discussed today. Unmute yourself and you can speak. Okay, leave. Tomorrow when we come, so we'll Monday we'll meet on Monday. So we can discuss. Okay. Thank you.